Now may I introduce the moderator, ASCE Texas Section VP Educational, Brett Pope.
Thank you all for joining us today for the Texas Section ASCE webinar, When Rivers and Infrastructure Collide. This webinar is the fourth in our series of monthly webinars for 2017. I'd like to thank the branches for hosting viewing sites all across Texas. As the State Association for Civil Engineers, we are happy to provide this service to the engineering community. If you're not a member of ASCE or the Texas Section, I invite you to become a member so that you can benefit from being a part of this professional association. Now I'm pleased to introduce our presenter for today's training. Stephanie Kaufman is a project manager in Friesen Nichols Water Resources Design Group and is a firm associate. She is a licensed professional geologist that specializes in fluvial geomorphology with an emphasis on stream bank erosion and channel processes. Stephanie received her BS in geology from University of South Alabama and MS in geology from Baylor University. She's currently the acting chair for the Texas chapter of the Association of Environmental and Engineering Geologists. Stephanie has over 12 years experience. She has conducted walking assessments over 400 miles of streams. That's over 800,000 steps on your Fitbit. Ms. Kaufman takes a resiliency approach to projects by anticipating change to identify and mitigate risks short and long term. Her project background includes evaluating stream stability and erosion, especially in urbanized areas, and developing viable solutions where road, pipelines, and structures that are in danger of failure caused by flooding and natural processes. She also assists with designing stream restoration for mitigation projects. Stephanie, take it away.
You guys hear me okay? I'm hoping so.
Yes,
I'm going to go ahead and roll. Excellent. Thank you. All right, and thank you, ASCE Texas, for inviting me. Today's talk is something that I'm really passionate about. The title of the presentation is When Rivers and Infrastructure Collide. And what we're going to be talking about is resilient design through geomorphic analysis. So I'm going to go ahead and just jump right in. So when we talk about resiliency, from a geomorphic perspective, because resiliency means a lot of things, but from a geomorphic perspective, the way that we would look at it is adjustments, they're common in nature. Nature changes. It's dynamic. And so resiliency is preparing for that disturbance, anticipating change, and be able to withstand or evolve to recover from that adjustment or that change. And then knowing your past, being aware of possible scenarios, aware of the potential for change, just understanding what's going on, that is very beneficial to anticipating and adjusting. And that is going to increase your responsiveness, and you can reach stability faster. So we're looking at rivers not just as a point on the map, we're looking at them as a system. That's what they're alive, they're living, they're moving through the landscape. They're not just a point on the map, they're not just a small reach, they're big basins, they're watersheds, they're connected. So for those of you who don't know what fluvial geomorphology is, I'm going to give you a crash course, so just hold on to your seat. And for those of you who already know what it is, this will be a really general refresher. So fluvial geomorphology, fluvial is relating to rivers, geo is relating to the earth, and morphology is the study of change. So we put it all together, and we're looking at how rivers change over the earth and how they're shaping and forming it. And this has been happening for millions of years. This isn't something that just came up. People have been studying this for a long time. But you think about how nature's been changing. Like I said, I'm a geologist, so think of the Grand Canyon. Millions of years to form. It's the processes that are happening today happened a long time ago. They happened millions of years ago. They happened thousands of years ago. Paleo, historic, hundreds of years ago. Engineering, our engineering lifetime, 25, 30, 50 years. And then even event-based. And the thing I like to note is that event-based circle, that is downstream of the Canyon Dam spillway. That happened after a rain event that lasted about 48 hours, 30 plus inches of rain, and it cut down many, many feet. And it happened very quickly. So it's really dynamic. Things are changing. So why do we study geomorphology? Why do we care? Well, because like I said, you need to expect change. It's natural. It's going to happen. And rivers respond to stressors, changes in our weather patterns, changes in the land use, where flow's going, sediment. All these different changes are changing how the channel is forming and shaping, and so does our infrastructure. As we build and encroach on our channels and our floodplains, that's changing. So if we can plan, we can allow and anticipate this change, and we can try to manage it. Nature's always going to be smarter than us, but we can try to work with it. And without resilient planning, results can be severe, and often they're very expensive. Things get shown. Our roads get eroded, our pipelines get eroded, big infrastructure, levees, what have you. So it's just being more forward-thinking, thinking of it as a system. So this is something I get really excited about. I'm a geologist, like I said. So geology and soils, that's the big thing that I'm looking at when I'm out in a stream. And the thing that I want to hit home on is you hear about geology and you hear about a layer. This is just an example from the Metroplex, the DFW area in Texas. And it's made up of all these different formations. And you have Eagle Ford and the Woodbine and the Grayson and what have you. There's a long list. But the thing that we need to think about and remember is that each one of those formations is made up of many different layers, different lithology, different stratigraphy. It has clays and silts and sands and shales. And what makes it so interesting and exciting for me as a geologist and geomorphologist is that they all erode at different rates. So I can't just say, the Eagle Ford erodes at this rate. No, it just depends on where you are. Are you in the upper or in the lower? Just understanding your geology, your position. And that really drives how the channel is going to form. Is it going to be threshold? Is it controlled by rock? Is it down cutting? Is it widening because it's in sand and sediments are more erodible? So it's really important. And geology of roads, that helps form our soils. So I could spend all day talking about that. Anyhow, the next thing we look at is landscape change. And this is also really exciting. As a geomorphologist, I love to look at the land and the shape of it and how water goes over it and look at the history of the time. How did it form? Because it's been forming, like I said, millions of years. But let's just dig into what we're interested in. Because most people, when we talk about geology, they don't care about millions of years. They care about the last 100 years. So let's look at some photographs of the landscape. You have 1952, 1968, 2015. This is also in the Metroplex. This is around Grand Prairie, Texas. And the one thing I like to always talk about is what the heck are the rivers doing? I don't think they know what they're doing as much as we don't know what they're doing. The reason is we've been farming and manipulating the land for 100 years, even before this was urbanized, before it was developed. So we have been changing our channels and influencing them for a long time. So understanding how they change through time is very critical. Understanding how the flow is getting to them, what's changing, what's going to change. The next thing I want to talk about is just meander migration. And the reason is a lot of people, when they think of rivers, they think of them moving side to side, just laterally. And which is true, they do. And some of them move more than others. Some move millimeters a year, some move feet, hundreds of feet. I mean, they're very dynamic. They move all over the landscape. And this is just an example from a quick desktop study of going, okay, what's this channel moving at? This is located in around College Station, and it's in a very sandy material, and therefore it migrates pretty quickly, a couple feet a year. But the other thing you need to remember is that channels don't just go back and forth, they go up and down. So they're changing, vertically and horizontally. And I'm not going to try to spend all day on this, but for those of you who've seen it, I'm going to do the quick refresher. This is just an example of channel evolution model. I'm using Shum, Harvey, and Watson. There are a variety of different channel evolution models. This one's just very simple for me to explain how channels change. There's 5 types here. And let's just envision the first one being type 1. That's going to be, let's say, channelized, because channelized means pretty plain Jane, pretty nice regular channel. So let's just say it's channelized, it's stable. Everything is happy and in balance. The water, the sediment, and the slope. Everything's happy. The balance is good. Then we think back to Lane's equation. And, everything is working. We don't have any net aggradation or degradation. But then a stressor occurs in the watershed. Something happens, whether it be more more water, less water, more sediment, change in slope. Something's happening that's causing an instability, and that causes channel degradation, downcutting. So the channel starts to incise. It forms a nick point. And if you see on the slope down here, the longitudinal profile, there's a nick point. And what that is, that's just a drop in elevation in the channel. Think of a mini waterfall. And those things usually start migrating upstream. And as they start migrating upstream, they start to widen. The channel widens out and it starts to undercut the toe. And that's when we're getting into type 3. And the thing I want to talk about is when you're dealing with an urbanized or an area that's becoming developed, you want to start thinking about channel evolution, especially between 2 and 3, because once you get to 3, it's usually encroached on your development. Either your house, your road, your pipe, some kind of infrastructure is being compromised. A lot of times we can come in and fix something or try to work with the river around 2. But once it goes to 3, it's very difficult. So if we're looking at protecting it, I'm not talking about restoring the channel, I'm just talking about protecting infrastructure. The best time to get in is between that 2 and 3. But now if everything was happy and the channel, everything was allowed to get back into a balance and you could work through the channel evolution, water, sediment, slope, everything is coming into a balance, you're going to have aggradation, sediment's going to deposit, vegetation would then become established, your velocities, everything is starting to equal out. You have a dynamic equilibrium until it starts again, because there's going to be another stressor, and it's going to channelize, and it's going to do the same thing again, go through the same progression. I also want to quickly talk about the photograph. On the side, you see here, there's a gentleman right at the nick point, and that's about a 4-foot nick point. And now if you were upstream and you didn't even walk downstream in this channel, you would never know. You'd think that's just a nice little blackland prairie channel. And you walk downstream and you see this waterfall. And this, just to let you guys know, I live on a creek. I love streams. I live downstream of this. So I monitor this. I'm a big nerd, and I've been monitoring this for 9 years now. It's moved over 70 feet. It's pretty fascinating. And I want to go to the downstream part of it to show you. Same nick point. If you look downstream, it's just widening out. Everything is widening, and you can see a pipeline's been exposed. But the other thing, we don't want to just talk about the channel and how the channel downcuts and widens and it changes. It's also systemic. It's affecting the whole watershed. So as the main tributary, the main branch of your river, your stream is changing, so are all the little tributary branches. They're all changing. They're all downcutting. They're all widening. So this just, the next set of photographs where it says watershed adjustment, you have a downstream, and you can see where it's basically in stage 3, it's starting to cut out that toe. And then you can see this is the one below it. That's a tributary that's just cut because it's trying to lower to the same base level as the major creek or the main stem. So you can't just think of it as a small reach. You can't think of it as a point on the map. We need to be thinking holistically, thinking more of that resilience, thinking bigger picture, thinking system. So, and what does this mean? Okay, to infrastructure, because the title is Infrastructure, Rivers Collide. Here's a good example. This is a 60-inch pipeline. The thing that when I went to visit this site that I take away is, holy heck, if it hits the pipe and the pipe breaks, who cares about the dinky channel that's here? We're going to have a whole nother big channel because this is a major water line, 60-inch, 5 feet. And that's huge. It'll cause a whole new river. We'll have a lot of bigger problem on our hands. So this is why we care about looking at a system. Another example, this is a major interstate highway pier. This bank right here is with the water depth about 25 feet, and it's cutting into that pier. So another big issue. Here's another example. This is a project that I've worked on before. It just has a lot of different issues. And this is common in an urban setting. You're going to see fallen, collapsed roadways, outfalls, there's a broken sewer line, and there's an amenity, a ballpark that can't be accessed, all because of channel erosion, stream bank erosion. So figuring out how can we fix all this and make it more resilient so it doesn't happen again, or anticipate the change as channels change. They're dynamic. And the last thing I just want to show you before I jump into a case study is how quickly these things happen. This is an example from a project that we looked at for a watershed study. We did a channel erosion reconnaissance where we basically just drove around this municipality, looked at where some of their issues were, ranked their channels, and this was a really interesting one. It ranked high, and you can see there's a lot of erosion. 2011, it's close to a ball, a ball complex, a football field, stadium, and there's a lot of erosion going on. And this is what it looked like in January 2011. And if you're from Texas, you know that after this, we went through a really big drought. We didn't get any rain. We got very little rainfall events. And this material, let's go back to geology, it's composed of the Eagle Ford shale. This stuff flakes, it weathers real rapidly, it's susceptible to wetting and drying. As things dry out, it becomes more friable and flakes and just flakes off. That's what it looks like. And if it's remained wet, it usually flakes at a slower rate. It's because you're keeping it at a constant moisture. So the bottom is kind of kept wet, and then it had a little bit of perennial flow. It's a perennial stream, so it had some flow. Flow was able to keep wet. The next picture, this is November 2013. You can see that in just 2 years, we lost over 8 feet of erosion. That's crazy amount of erosion. The thing that I want to talk about is those two flow events caused that. There's a lot of material gone that's contributing to sediment loads in the watershed, but that's also encroaching on that infrastructure that's up on the top of the bank. You've lost the head wall, but you notice the bed didn't really downcut, just the side. So this channel was laterally changing. So it's understanding how is that going to change, and then anticipating that if we protect that side, where is it going to change? It's probably going to change on the bed. So we made it incorporate some kind of protection on the bed as well as the banks. So let's try a new approach. I'm all about a multidisciplinary team. You know, we all need to be working together. We all have special skill sets, and to make these projects, you know, sustainable and more resilient, you got to have everybody in there. We're all pieces of the pie, and so if you have biologists, geologists, engineers, hydrologists, everybody working together, it makes for a really good project. And you're more holistic, and you're prioritizing, and then it's always good to integrate the stakeholders too. So I want to talk about a case study. This is on the Brazos River, and this is an example of some stream bank erosion near a major roadway. It's one of a few major hurricane evacuation routes that evacuate the area of Houston. And you can see there's a whole lot of bank erosion. This is the Brazos River, and it's no stranger to bank erosion. And you can also notice not just the roadway, but there's also levee in the background, and there's neighborhoods and parks and everything in the vicinity of this. So for those of you who want to know kind of where I'm talking about, here's the state of Texas. We're down near Houston. This is approximately where the site's located. We're looking at about 25 miles of channel during this study. So the star here is just zooming in. I wasn't going to bore everybody with the 25 miles of channel, even though it would be super exciting for me. But here is just looking at aerial photographs and digitizing left and right bank, looking downstream, top of the bank, and seeing how it's changed over time. And the dashed line, that is 1953, and the solid line is 2016. And it shows how they've changed over time. And you can see in some locations it's changed hundreds, if not almost 1,000 feet. And so not a lot of times went by, a lot of movement. So channels are dynamic. The thing I want to talk about again, I live by a stream. I love it. Everybody does. Look at this. You can see people want to live near it. What we got to figure out is what's the balance? You know, what is the balance that we do? Because, you know, things that make everyday life possible, from our roadways that get us to and from where we need to be going, from our pipelines that carry our water to us and away from us, and our parks that we have fun in, and our levees that keep us from flooding. All these things are in close proximity to our rivers and our streams, and it costs money to fix them. So how do we figure out the balance to work with them? And so you got to keep these in mind. So jumping right into looking at the geology and geomorphic setting. That's something that I spend a lot of time on. That's what I'm really interested in. I want to know, how has that channel changed through time? And this is a nice example of, this is an elevation map using LiDAR data 2014. And the red is higher, and the green is lower, and there's a little bit of white down towards the bottom, whitish green. That is lower elevations. The things that I like, I'm going to show you guys with my mouse. I don't know, hopefully everybody can see it, but this is right here, the valley wall. You can see right here, nice valley wall. And you can see how big those meanders are on that old, up against the valley. So a long time ago, the Brazos was a really big river, and it formed very big meanders. And so we want to understand the past. Remember, we're talking about resiliency, so we want to know where was the river, and then where did it go? And then, so as it formed this giant plain, this big floodplain, this big valley, huge, then the slopes were decreased. There's a lot of sediment in there, and the channel then, if you notice, up to the north, there's another channel. That is Paleo-Brazos. That's an older Brazos that's now occupied by Jones and Oyster Creeks, but that became the Brazos River. And it's much smaller, and the bends and the sinuosity are smaller and tighter, and that's because it had a lower slope. And the thing that, and then this river right here, this is current day Brazos. And the thing that I like to look at and take away from this is it's interesting to look at why the river is doing what it's doing. How are we going to anticipate what it's going to do in the future? And it's really neat when you look at the form. It's following the same alignment. You know, here's the old one, the paleo, and here's the recent one today. And it's almost following the same alignment. And where the old one went up, so did the new one today. And wherever it went down, so did the old one. So those are all interesting things. Thinking of the system, how is it going to work? How is it going to change? What are the other controls that are affecting this? You know, there's stormwater being put into the channel. There are floodwaters being kept in the channel. There's water being taken out of the channel. There's subsidence going on. There's saltwater intrusion moving up. There's a lot of things. This is a system. It's alive. It's living, and it's changing. And you got streams that are cutting up north. So locations that aren't levied. So you're having to look at this thing as a big picture. How is it going to change? How is levees going to affect it? How are more water being taken in or out going to affect it? And I just think it's really neat. The other thing is right where the location that we're interested in is right, it's basically going into coastal river processes. It's changing. And then as you get further down, you're going into more delta processes. So that's what we're looking at. You can't just look at the spot on the map. So areas of interest, I just want to show some photographs of what this river looks like when you're down in the boat. I was really excited that I got to take a boat ride, river ride, and with the team. It was a lot of fun, and got to see all the geology and all the erosion. And I know erosion's bad, but I really like it, so it's very exciting. This photograph shows one of the bridges that cross over the Brazos River, and you can see here, oh goodness, I want to go back. There is some tagging right here. The land used to be right here, and this used to be the whole bank slope, and now it's gone. It's all it's all receded, went eroded away. It's gone. It's over 120 feet. You can see that people used to access this. There's all kinds of tagging. The other thing that's going on is there's homes built, adjacent to it. There's all different types of processes, erosional processes. These are normal. They're natural. Stream banks slump. They fail, they erode, that's what they do, they deposit, and this just shows one where, some people are trying to fix some of the issues that they're having. There's pump stations that are located, pump stations that are taking water out, intakes, and, how are these going to be affected? How are they changing the system? There's also sand and gravel mining operations. How are they changing the system? The other thing is, I mentioned it earlier on the channel evolution, is that it's systemic, so through time, the channel's changing, the main stem's changing, so are all the tributaries. And this is a tributary of the Brazos. And you can see that it's slumping, and it's eroding, and it's going through the same processes because it's translating upstream, up the tributaries. And this is upstream of that same tributary. And you can see that it's been protected. There's a stormwater outfall there, and it's just going to keep eroding. I mean, that's what it's doing. It's changing in response. So it's a large system, and it's all playing off of each other. So I don't want to spend a lot of time looking at all 25 miles, but I wanted to just show you that during these trips, when we go out as geomorphologists, what we're looking at is the erosion, the geology, and all the things that are really exciting to me that I thought was really cool. And this one is when we floated it, there was, we saw the Beaumont clay, and we saw Holocene, really recent sediments, 6,000-year-old less, a lot of deposition. And the really cool thing is you can tie the type of failure you see to the type of geology. So wherever we were seeing Beaumont, if we saw Beaumont clay, a lot of times we saw a lot of translation slides. A lot those were the ones that move more horizontally. And then wherever we saw more Holocene, more recent depositional, we saw a lot more slumps and rotation type failures. And so this, if you weren't lucky enough to take a boat ride, this kind of walks you through it, but you see where there's bar development, where there's sand moving through the system, where there's erosion, where there's benches, where there's terraces, where there's the rotation and translation type. And why that's so important is the geology can help us predict what type of failure we're going to see, because it can help us then with design. It can help us understand what the river's doing, where it's going. And so this just shows a couple different photographs of the erosion that's happening, the deposition that's happening, and other types of stability measures that have been put on, protection measures on the channel. So going into the analysis after we've done all this field data collection, got to see it firsthand, looked at it. We also did a desktop analysis. We looked at aerial photographs, looking at 1953, 77, 89, 2004, 10, and 16. And we used a method that looked at putting circles, and I think this is the next slide, circles just like this. And this was after Legacy. What we did is to make it more reproducible, we used circles on the meanders. And the reason is, if I was to ask Bob and Susan, hey, can you trace the outer bank of that meander? Chances are our results would be very different, because where they saw the top of the bank versus where she saw the top of the bank may be different. So we tried to use a method that was more reproducible, looking at circles. The circles were positioned on the bend of the meander on that radius of curvature. And not to say they're exact, Bob and Steve may not have the exact ones, but it's probably a little bit closer. And once the circles were placed, then we placed the centroid in the middle. And what this shows us is how the meanders change, how they are changing through time. And to us, this is really cool, because we get to see how they're responding. How are they rotating? They're alive. They're rotating. They're translating. They're moving. They're shrinking. They're growing. What are all the things that are changing them? Does infrastructure affect them? Does bridge crossings affect the growth? Does vegetation? Those are the things that we're looking at. What's keeping them from growing? Are they translating downstream? Are they rotating downstream? Are they all shrinking, getting bigger? Are they going to cut themselves off? Those are the things that we're looking at. So by doing this, we got a whole lot of maximum outer bend migration rates. I don't want to spend too much time on the table. And then we also got the radius of the meanders. And this is all really useful information, because it helped us predict what these meanders were going to do. And we used another method by Hill, 2009, and this was really unique. It looked at, we picked data that we had, we felt pretty confident in, just from the 50s, 70s, and recent 2016. And remember, this is science, so it's not exact. This is using those circles and predicting where it's going to be. And so we were predicting out, using the same amount of years between what we have, predicting out to 2048. So the solid blue line is saying, in 2048, this may be where meander bends might be. And there's a big prediction error that goes with that. And so that blue, light blue buffer that you see, that means it could be plus or minus this. So, but that's just to show it's science. So we're just understanding, what is it going to do? Well, we took that data, and this is where the artistic, I feel like a lot of geologists are artistic, and you're having to interpret what you have, your science, your data, and say, well, if we use those circles and those meanders and the current alignment and the widths and depths, and we didn't see that the width of the river changed much in the amount of time we had. So if we assume all those things and everything kind of stays constant, maybe this would be the future alignment in 2048. But it gives us something to go by. It gives us something to use and predict what's going to happen on the river. So this is where that more resilient approach, looking at the system, looking at how is it going to change over time, so we can anticipate and we can be forward thinking. So this is where the multidiscipline approach comes in. The next thing we did was we used bathymetry, and here's just an example of the bathymetric data. This is water depth in feet below the water surface, and this was converted into elevation. And this was really neat. We did it all long stretch of channel on the river. And the really cool thing is, through talking with landowners and through the bathymetry, you know, at this one bridge location, there was a large scour hole. And talking to some landowners, they said that scour hole had been there for a long time. And it wasn't a result of the bridge. And which is nice because a lot of the other meander bends we have also had these same scour holes, almost at the same depth. So it was really neat. Now, we all know, like as a geomorphologist, meanders have scour holes. They have large pools on them, and they're deep. Obviously, infrastructure causes more localized disturbance and additional scour. So we're seeing that. But it was really neat to get this data, and then this data was then incorporated into the HEC-RAS 2D modeling. And then what happened from there is, so we used the revised bathymetry, and I have two figures here. The one that's on the left, that's the pre-existing, that's with as is using FEMA, and that's without the bathymetry data. That's not seeing any of the channel changes down below the water surface. And you can see pre-existing and existing, and you can see the amount of change. And so revising this bathymetry, you can see new conditions. And the cool thing about the 2D is you can see these hydraulic changes in the density and the flow vectors and different stressors. And you can see that when you look at using the bathymetry data, you can see how the flow vectors have changed. You have more eddies, you have more variability, and that's understanding really what is that river doing, where is it doing it, where is it moving sediment, where is it moving flow, where is the erosive condition, where is the stress going up. So it's a really neat tool. Having bathymetry is so useful. I think it's great. Then the next one is just showing it at a higher, that's still within the banks, and you can just see the amount of change in those flow vectors. So it's just another important tool. And why it's so important from a multidiscipline approach is when you start integrating all these things, we start integrating the morphology of that channel and how it's changing, integrating it in with the 2D modeling. You get to really see how is that river functioning, how is it alive. The next thing is we did some geotechnical. We had some geotechnical findings, put some borings out, and we have a lot of cross sections. And the reason we chose, we have B6 and B7. The ones that I'm going to talk about are highlighted in red. And B6 and B7, because those are the worst case scenarios. They have the steepest slopes, and I'll show a photograph in the vicinity of B5, which is just upstream of B6. And then B3 and B12, because those were the midpoints between the end of our study reach. So we didn't want to go to the extreme end. We want to go somewhere in the middle and get a nice average. So this is an example. This is the field team out during when we did the boat trip. And it's a really steep bank, and that's me up there. I'm exactly 5 feet, so I feel like I'm a pretty good scale. And that's a really steep bank. It's like a belly crawl up there, and the person taking the photograph is on the boat. So you can just see the amount of bank material, and you can see the geology and how it's failing, and it's really neat. That just gives you an idea of what we're dealing with. The really cool thing as a geologist, when we get to work on these types of projects where we have borings, so you get to see the boring and you get to see the profile, is really cool because you get to see the geology of what it looks like coming out of a little tiny hole versus what it looks like on the bank, and you get to line them up. So it's really neat. So as far as geotechnical findings, so we did some slope stability, 4 cross sections, and we did multiple loading conditions. And the reason we did multiple loading conditions was to understand the slopes under different water conditions. Because the steady state, that's looking at rivers during constant level. How is seepage affecting the slope? The transient seepage, that's looking at bigger, high magnitude flood events. For this area, we use the tax day flood. So if you're from Texas, you probably know what that means. But it was a very large flooding event. And then rapid drawdown. That's critical, especially if you have clay layers. That's because water rises so fast and it drops down really quickly. It doesn't give the clay enough time to drain, which leaves it more susceptible to failure. And then we also looked at deep and shallow failures, and that's basically looking at the geometry and how the failure develops, and then tension cracks. If you see tension cracks, that's a good indication that there's going to be failure. We're looking at how deep they are and then where that failure plane is going to occur. And so taking all that data together, you start to develop concepts. And these are extremely draft concepts, but it's just looking at what could you put in the river? What could be placed in there that, are you looking at more of a wall? What's that going to do? Are you looking at something that's using benways or groins? And what's that going to do? And by having that model data and that geomorphology data, you can put all those together and start looking at how the channel is going to change with time. So putting this thing in to protect this infrastructure, how is it going to affect the river upstream and downstream? How is it going to change it in the center of the channel? Protecting a bank and not protecting the other bank. What's it going to do? So, and then the last thing, I got through that pretty quickly, that I want to leave everybody with is that channels, rivers, they're systems. They're big and they're alive, and like I mentioned, the things that make everyday life possible are in close proximity to them, and they all play a part and a role in how channels change and how they're affected. And so keep in mind that when you're doing these types of projects, that one thing affects the other. You have to have a balance. So with that, that's the end of my presentation. I know I went through it pretty quickly, but if there's any questions, I'd be happy to take them.
Can the audience get a copy of your presentation, Stephanie?
Yes, sir.
Okay.
Actually, just to let you guys know, I gave this in front of a live audience, so there's going to be a question and I'll repeat it.
Did you all look at? Yeah.
So the question was, did we look at preliminary modeling efforts with each of the designs? So we looked at the river as is. Is that what you're asking? We looked at the river as is without any structure on it, and then looked at it with different design, the slope configuration. And then looked at different areas like adjacent. If you were to move a sandbar, what would that do in addition to stabilizing the bank? And then different configurations, do you want to do one whole huge smooth bank, or do you want to do some river training techniques in the smooth bank, or all river training techniques? Those are all the different things we looked at.
We do have a question that came in. Are there any plans to address the erosion by the bridge shown in the presentation?
Yes.
And then another question, can you talk a bit more about your designs?
So right now, so the designs, we've looked at just a variety of different types of designs, meaning if it would be stair-stepped, if you would have a benching or terracing look to it. We've looked at a variety of different river training techniques to push the flow out towards the center of the channel. Looked at techniques on how, on the adjacent, at this location, there's a sandbar, and if you were to manipulate the geometry and how that sandbar is, how would that affect it? So it's just been a lot of different modeling on the configuration to see how it changes the velocities and shears and the erosion, to this bank, and then what it would do downstream. I'm hoping that answered the question.
Okay. Are there any more questions from your live audience?
Do you guys have any questions? Hold on, yes.
How did that affect the geotechnical analysis, the ability of the slope kind of switching back and forth between facts like water differences or water loading in those different units? I would expect it would make it a lot more unstable.
So the question was asked was, did we put in the differences in the stratigraphy, and how did it affect the model? And yes, we did. Here's just an example that shows some of the riverbank cross sections, and it's looking at the steady state steepage or with tension crack, and it shows the different lithology that was encountered in the borings and the different water levels and how they affect failure and how the failure mode differentiated between them. So to answer the question, was the failure mode different? Yes. Did the geology affect it? Most certainly. And the water, whether it be in rapid rise or drawdown, it affected the results. So you had different, yes, keeping different lithology mattered on this project.
And then this talk a lot about kind of the resiliency approach to the existing problem. Can you talk a little more about it?
We've got two more questions. I'm not sure if you're still answering your live audience.
Go ahead with the two other questions, and then I'll address. We do have another question, but I'll address the other two.
Okay. Did y'all find a correlation between the soil type and the degree of erosion?
Yes. So we didn't do like erosion rates per se. We didn't look at it as, this many inches per year or feet per year. This was a really high level study, but where we did see the Beaumont clay, we expected very large failures, a lot of erosion where it left the banks vertical, really steep. And so we'd expect to have a lot more loss in those locations. And then wherever we saw more recent materials, such as the Holocene sediments, those were more slumps, and a lot of them were still vegetated. They were slow-moving creeps and like rotational type slides. So still having loss, but not a lot.
And then let's see, we have another one after this one too. How has the construction of large reservoirs in the Upper Brazos affected the Lower Brazos since 1940?
I did not spend much time studying that on this project. It was a question that came up. We were looking at, because it does have the controls on it, so it does change the flows downstream. A lot of flow stays within the channel. I think, from looking, we did look at it, but from looking at it, it has changed and slowed the progression of the meander migration down quite a bit, because it's not having the large flows come down, is what I'm assuming. But I didn't spend much more time other than that. We knew that, hey, after this time, this occurred, and this is likely what happened. A lot of it was just from literature review.
Okay. And
Yes,
we'll do one more. And
Impoundments do affect it, so.
yeah. Do you think the erosion was being caused by the increased flows through the watershed? And did you look at a watershed solutions?
So no watershed solutions yet. That would be a next step. I would love to do that. So haven't done that yet, but did look at talking about the type of water coming in. So what we looked at is just what were triggering the types of failures we were seeing. We were definitely interested in coming up with ideas on, hey, these are locations where water is being taken out. These are locations where water is being put in. These are locations where there's sand and gravel mining operations. So we looked at how is that affecting the channel, and we haven't dug in much more than that, just saying that, hey, these are points where we're seeing these influences. Do we think they may have a bigger systemic problem, or are they just a blip on the screen because the river's so big? My experience working in smaller streams, they have had an effect, but the Brazos is a large river system, and so sometimes putting, it's almost like having a 5-gallon bucket and you stick your finger in it and you take your finger out and it really didn't change it. So we see a lot of that, but I would love to look at this from a more basin-wide, larger system approach.
Okay. Any more from your live audience before we wrap up?
No, I think we're good.
Okay, well, excellent presentation, Stephanie. I really appreciate it. Thank you again for participating in today's ASC Texas Section webinar. As mentioned before, individual registrants should receive an attendance acknowledgement without further action. For those attending with a group, the site coordinator will receive a PDH certificate for distribution. May's webinar is Drainage Infrastructure Analysis, Identifying the Worst First. I invite you to visit Texas Section webinar, texasasce.org, to register for the webinars, to learn more about the association, and to take advantage of the benefits of membership. You can also watch 2016's recorded webinars on demand and earn PDHs. I'm always available for your questions and hope to hear from you soon. Thank you for your attendance. Have a great day.
This concludes today's webinar. Thank you for joining us. The session will now close.